Moving right along, Elad Zinger from Hebrew University, penetrating streams stir up the inner ICM of galaxy clusters.
Okay, can everybody hear me? I guess so. Hello, so my name is Elad Zinger. I'm from the Hebrew University, and this is some of the work that I've done in my PhD, which I've just completed several months ago with Avishai Decker, and that means I'll be applying for jobs later on, so keep an eye out for me. This is work I did with Avishai, Yuval Birnbaum, and Rick Hafthoff, and Diskin Nagai, and there's a paper which is almost going to be submitted soon, so look out for that as well. And what I'm going to tell you about today is the penetrating gas streams into the ICM of clusters. So before I start, I just want to tell you that clusters, usually observationally, are classified into two groups, relaxed and unrelaxed. And the way you do that is by observing the clusters. So this picture is a picture of one of the clusters from the simulation suite. And ignore the colors for a minute, just look at the black contours. That's kind of a proxy for the X-ray luminosity. And unrelaxed clusters are clusters where you see a lot of, more than one central X-ray peak. You can see that there are two X-ray peaks here. And the isophotes are not very regular. And if you look at the centers, they're shifting all the time. And there's some filamentary structure which is usually associated with gas which is stripped from the satellites. Whereas relaxed clusters look much more nice and regular. You still see a little bit of substructure, which is all to be expected, of course. But you don't see this big mist that we saw before. And what I'm trying to show here is to see another reason for the relaxed-unrelaxed population dichotomy. And bearing in mind that up until now, most people think that it's simply a matter of mergers. If you have mergers coming in, you're going to get an unrelaxed system. It's as simple as that. And we'll see that maybe it's not that simple. So we used a suite of simulations which were run by Andre and Deske a while back. We have 16 clusters. They have all the usual ingredients thrown in. One important thing, there's no AGN in these simulations, and that's a good thing, because if we had an AGN, we might not be able to see the effect of these gas streams. So this way we can really isolate the physics having to do with the streams themselves. And after they ran the simulations, they took them through this classification, which was really trying to mimic the way observers look at clusters, and then they found a relaxed and unrelaxed classification for these simulated clusters. And we wanted to study that. So to do that, first of all, we started to look at the simple state of the system. We used a generalized G's equation, which is basically a motion equation for the spherical shells. And this equation we have on the left-hand side, this is just the full convective derivative for the shells. And on the right-hand side, these are the different force terms. So we have a gravity term, a thermal term, turbulence, and terms which have to do with anisotropy and sphericity. And using this equation, if we look at this equation and apply it to the clusters, we can maybe learn something about their dynamical state. So we notice that, come on, there we go. If a system is in steady state equilibrium, the left-hand side is going to be equal to 0. And then we can get this simplified equation with you have the thermal and non-thermal, where this is the thermal term and these are the non-thermal terms, divided by gravity should be equal to 1. That's if you're in steady state equilibrium. So what we did, we looked at these terms and we averaged them over the relaxed clusters and the unrelaxed clusters, and this is what we got. We see that for the relaxed clusters, the sum of the thermal and non-thermal terms balance out the gravity, and you see that it's equal to 1 over most of the area. For the unrelaxed clusters, the systems are not in steady state. You can see that they're dynamically unrelaxed. There's something going on there. And the reason for that, if we look at the two terms, we have a thermal term, which is pretty much equal across the two populations. So the real culprit here is the non-thermal term, which is higher by about a factor of more than 2 in the unrelaxed cases. And if we break that down, we see that if we break down the non-thermal terms and look at the different contribution from turbulence or from the other two terms, the anisotropy and asphericity, we see that the turbulence is usually the most dominant form in the unrelaxed clusters. So we're seeing here that the unrelaxed clusters not only observationally are unrelaxed, but also if you study the dynamics, they're unrelaxed. And if you look at the outflow, at the mass accretion into these clusters, we also see a difference between the unrelaxed and relaxed populations. The unrelaxed have much higher inflows and outflows than the relaxed clusters. So we get in this picture of unrelaxed clusters having more outflows, and these are churning up and creating turbulence in the center, which leads to the unrelaxed state. Great. So how is this mass accretion going into the clusters? Well, when we looked at that, we found out that we found these gas streams. We found that most of the accretion, what we have here is a picture of a typical cluster. This is the mass inflow rate, this is density, the entropy and temperature, and the white circle, that's the virial radius, okay? We see that most of the accretion, almost all of the accretion, is along these streams, very, very well-defined filamentary streams coming all the way into the cluster. You can see that they're denser than the environment, they're slightly lower entropy, but they're not much cooler than the environment. Okay, you can see this line out here, this is the accretion shock, and in clusters the accretion shock extends out to at least 2 or 3 times the real radius. And you can see though that inside the shock, the streams aren't cooler than the environment. These aren't cold flows, these are warm streams. And what happens is that for clusters at low redshift, the mass of the clusters are already m star, roughly, and they'll typically reside within thick filaments which are as thick as the virial radius. And at this time, these filaments have already developed virial shocks of their own. So the gas has actually been shock heated entering into the filaments and shock heated within the filaments by smaller shocks. And by the time it enters the cluster, it's already more than 1,000,000 degrees. So the cold flows that we all know and love at high redshift evolve into warm streams by the time we get to redshift 0. That's an important understanding. Okay, so let's look at these streams now and focus on them. So we found out that these streams sometimes penetrate into the very, very center of the cluster, undisturbed. And this is one case, and once again, this is the virial radius, and this black circle just denotes 25% of that. And if we look at this stream, we can see, that it penetrates all the way to the center, actually overshoots the center, that's why the color changes here, and it shocks with the gas from the other side. That's a very, very dramatic accretion that happens right in the very, very center of the cluster. But that's not always the case. In roughly half the cases, we actually saw these streams come in. You can see a very nice stream coming in from here and from here, but they don't reach the center. They're stopped outside, and the center area is just dominated by these random motions. If you look at these clusters over time, we can see some cases in which the cluster initially has streams which do not penetrate to the center, but then later on penetrate all the way to the very, very center, as we see here. And sometimes it's the opposite. Sometimes streams which penetrate at earlier redshifts all the way to the center have been pushed back by redshift 0. And this penetration seemed to be important for us for understanding how the relaxed and unrelaxed classification came about. But in order to do that, you can't just look at these slices, these Cartesian slices. You actually have to look and look for these streams everywhere. So that's why that's why we built these hammer projections. We just looked at spherical shells, and what we're seeing here is a movie of these spherical shells as we move in from the outside all the way to the inside. The top flux is the mass flux, mass inflow rate. Bottom one is entropy. And let's look at this again because it's a cool movie. So wait a second. So this is outside the virial shock. We're outside of the cluster right now. You can see these are the large-scale cosmic web filaments coming from the outside. You can see that they're already surrounded by a shock here and here. They already have shocks of their own. You can see the imprint of the large-scale pancake. And then we keep going in. We're going through the shock right now, and we're going down to the center. You can see that the streams forming, and we can follow them all the way into the center and see that they actually penetrate to the very, very center, at least in this case. And on average, we find that most clusters have 6 or 7 streams, but only 1 or 2 really go deep and penetrate to the very center. So this is the most important plot in this case. And what we did here, we're plotting the maximal penetration, the stream that penetrates all the way, the maximal penetration at redshift 0 versus redshift 0.6 for the entire population, entire suite of simulations that we have. And we see some very interesting things. Let's just look at the x-axis now. And we can see this is just a rough line for where 25% of the virial radius is. And we can see that at redshift 0, all these red points are unrelaxed clusters. All the blue points are relaxed clusters. These are clusters which were unrelaxed at high redshift and relaxed at low redshift, and this one is the opposite. And you can see that at redshift 0, all the unrelaxed clusters have streams which penetrate to within 25% of the virial radius, even most of the time even to within 10% of the virial radius. And all the relaxed clusters have no streams which penetrate deeper than about 35%. If we look at redshift 0.6, we pretty much get the same picture. We see that below this line, we have all these unrelaxed clusters. There are 2 anomalous cases, this 9 and 103, but you can explain that by the fact that maybe these are unrelaxed clusters not because of penetrating streams, but because they're undergoing a merger, and that is indeed the case with these, or at least one of them, I think. This one, however, this is a bit of an anomaly. We have a cluster which seems to be unrelaxed at high redshift, which seems to be relaxed at high redshift, but has a deeply penetrating streams. That might be a misclassification or I'm not sure what it is. But in general, we see a very, very strong connection between penetration depth and dynamical state. And the coolest thing is these 3 points, because these 3 points have deeply penetrating streams at high redshift, and they are unrelaxed at that redshift. But by low redshift, the streams have been pushed out, and as a result, they've also gone from being unrelaxed to relaxed. And we can see the changes in the penetration also correspond to changes in dynamical state, which is great. Finally, a few more streams. I don't have time to go into this because my time is short, but if you can ask me about these streams. If you calculate kind of a rough calculation, you can find they can bring in a lot of energy. A huge amount of gravitational energy can be brought into the streams, 10 to the 45 ergs per second, which is roughly the total output of the cluster itself. So this is really a lot of energy which can come in with the streams. What it can do in there, that's a different question, but potentially it can be an important effect inside the central regions. In addition, as you can see, this is the same stream collision that I showed you earlier, so they can generate shocks and cold fronts in the center. And I have a whole paper devoted just to figuring out how streams can create cold fronts in clusters. So it's another cold front generating mechanism in clusters. So that's it. Those are my conclusions. The one thing I want to talk about a little bit more here is the fact of this cooling flow problem, the cool cores. We know that cool cores are usually found in relaxed clusters. And now that we know that relaxed and unrelaxed will also be tied to penetrating streams, this might give us a better understanding of how maybe to alleviate this issue of the cool cores, because the turbulence generated by the streams can be an important factor in distributing the energy of the AGN, maybe solving this problem. Thank you. Thank you.
So, while Colin DeGraff sets up, any questions for Elad? David Elbaz.
Thanks. Have you calculated the impact of the entropy injection associated to the energy of the infalling matter onto the cluster? You know, there is an excess entropy in clusters as compared to the gravitational collapse alone. Does it help solving this issue?
A little bit. I did calculate the entropy a little bit, and it seemed to point in the right direction, but it wasn't very significant. And the problem with the simulation is that I can't really follow it, time step by time steps, because it's kind of an old simulation. But I am planning to look at more detail and more up-to-date and more detailed simulations. So, yes.
Have you checked the impact of the cold streams with respect to the gas mass fraction that you find and the gas mass fraction profile? And is there a dichotomy in terms of gas-rich clusters in the center because of the cold stream versus gas-poor?
Okay, first of all, these are not cold streams. They are warm streams. No, I have not, but I will. That's an important point. I will look into that.
So you define the relaxedness purely in terms of the kinematics of the gas, which is not necessarily what observers do when they look at clusters of galaxies. So in order to make that link, it makes sense that this same stream will also impact the overall dynamical relaxedness of the system if, along with those streams, also comes in dark matter. Mm-hmm. So to what extent does the dark matter follow these gas streams in terms of penetration depth in particular? Have you looked into that?
I wasn't able to look into that in detail in these simulations because they don't have the velocities of the dark matter particles. But in general, the dark matter isn't as well defined as the gas streams. So I think the gas streams penetrate much more than the dark matter. That would be my guess.
Okay, let's move on. Let's thank Elad again. And I want to thank Colin in advance